it going? Can't believe there's only 2 weeks of the semester left.
That's too close.
Yeah. 3 if you count finals week, but I don't count it. I'm not envious of you guys with your finals. But yeah. So again, the plan today was just to, did I start this? Yeah. The plan today was just to talk about exam 3 a little bit. I have no idea how long this is going to take. Maybe we'll do a little bit of elliptic geometry. I don't know, but of course, exam 3, I've already posted some of this on Canvas. It's of course Friday of this week. What's today's date? The 19th, so that makes Friday, what, the 23rd? And it covers hyperbolic geometry. All right, so this is 6.3 through 6.7 plus all the additional stuff we talked about. And the format will look really like previous exams, right? Problem 1 is just going to be some true or false things, probably 5 true or false problems. Then we've got problems 2 and 3. These would just be basic theory, short answer type questions, maybe state a definition or a theorem, something like that. So basic theory, short answer stuff. And then, as we've done on previous exams, the next 2 problems, 4 and 5, would be short proofs. Honestly, I haven't written the exam yet, but I have thought about it some, and I might struggle here to find good proofs to put on this exam. It might well be the case that it might well be the case that problems 2 through 4 end up being some short answer things, and there's only 1 proof, but we'll see. Any questions so far? All right, so let's just recall all of these sections and the important results. All right, so 6.3. 6.3, what was this? This was the beginning of hyperbolic geometry, really. We had the hyperbolic parallel postulate. What is the hyperbolic parallel postulate? Remember, we stated it really in terms of the angle of parallelism, right? We didn't go with sort of the more obvious, given a line and a point, there's more than one line through that point that's parallel, but we proved immediately that it's equivalent. But the hyperbolic parallel postulate is that the angle of parallelism is strictly less than 90 degrees. And again, I want to remind you that the angle of parallelism is not some universal thing for all lines and points, but it's defined for a line and a point, and for a different line and point, you might have a different angle of parallelism. But this is a statement that no matter which line and point you choose, it's always less than 90. All right, so this is defined for a line and point pair individually. in this section, we just talked about some of the consequences of this. So you should know all the consequences of assuming this parallel postulate. For example, if you assume this to be true, then immediately you have non-Euclidean results. Things like rectangles don't exist. I'll use some notation here that we introduced, I think, in the next couple of sections, but the angle sum of a triangle is always less than 180. And we had lots of other consequences, things like, how about parallel lines? Parallel lines are not everywhere equidistant. Etc. Lots more consequences of this. But you should be familiar with these things, right? This comes into the basic theory type stuff. So then we talked about 6.4, which really doesn't feel that long ago at all, but 6.4, then we got into hyperbolic polygons. Hyperbolic polygons. And the most important thing here, absolutely the most important thing that we talked about with hyperbolic polygons, we introduced the concept of a defect, right? So this is just sort of the amount that your polygon fails to be Euclidean. Right? If it's got a large defect, then it's really not Euclidean because the angle sum isn't even close to what you would expect in the Euclidean sense. So we introduced a defect. And using that, then we had a notion of, in fact, not using defects at all, we had a notion of equivalent polygons. These are polygons that can be cut up into triangles, and then all those triangles can be rearranged to look and is that how I should phrase this? Yeah, I like that. I like that thought, right? So these are polygons that can be cut up into congruent triangles. Those triangles can then be rearranged so that one polygon can be rearranged into the other one. That's sort of how I think about it. We had equivalent polygons. There's another really interesting result here. AAA is a hyperbolic congruence condition. So we proved that in this section. Really interesting result that there are no similar triangles in hyperbolic geometry. If you're similar, then you're automatically congruent. And one more really important topic from this section was the associated Saccheri quadrilateral. These are used all the time in proving things. And the most important point here is that the associated Saccheri quadrilateral for a triangle has the same defect. All right, so same defect. And coming back to equivalent, obviously congruent is a stronger condition. So if you're congruent, you must obviously be equivalent. though congruent is obviously a stronger condition, we ask this question of, are they actually not, is it not strictly stronger? Are all polygons that are equivalent, are they perhaps maybe possibly congruent? And we showed with a counterexample, just with a quadrilateral slice into two, that that's not necessarily the case, but we did show that if two triangles are equivalent, then they must have the same defect. And vice versa. If they have the same defect, then they must be equivalent. All right, so a really, really important result there is that these two concepts that seem very different are actually the same statement, really, right? They're equivalent statements, and triangles being equivalent is the same as saying that they have the same defect. So that's somewhat surprising, and of course your homework was to argue that it's not true just for triangles, it's true for angulons in general. Oh, by the way, I'll point out absolutely the most important thing about defects is the fact that this is additive, right? If you cut up a polygon into different pieces, the defect of the original polygon is the sum of the defects of the smaller pieces. Any questions? All right, let's keep going. Just reminding you of how this stuff works. Then really not long ago, now we've got area. So 6.5. Hyperbolic area if you want. And I'll just remind you that however you define area has to have three different properties, right? It has to satisfy SMSG 17 through 19. So one, every region has a unique area. So no matter what you define your area to be, it should give you a unique value for every given region. Two, congruent triangles all have the same area. So again, no matter how you define area, this better be the case. If two triangles are congruent, they better get the same value assigned to them. And three, perhaps the most important, they all have to be satisfied, but it's got to be additive on partitions. All right, and your last homework problem was asking why we define area to be the defect and not perhaps the angle sum. Right? Well, if you define the area of a polygon to be the angle sum, sure, property 1 is satisfied. Every region has a unique area. Every region has a unique angle sum. 2, if I define the area of a triangle to be its angle sum, do congruent triangles have the same area? Well, congruent triangles have the same angle sum, so yeah, that'll work fine. But property 3 doesn't work, right? It's not additive on partitions. If I slice this triangle into 2, the angle sum, which I'm calling the area of the larger triangle, is not the sum of the angle sums of the smaller ones, right? So area doesn't work. We don't have this additive property if we use the angle sums. That's why defects came in and were so important here. And not much else to say about this. Just remember that the area of a polygon is defined to be k times the defect. where k is just some constant that you choose. It's some fixed constant that's fixed in the geometry forevermore once you choose it. All right, it's just a scaling factor. And then we come into models. Hyperbolic models. Really important stuff because this finally proves that everything we've been doing has been worth doing. In other words, it proves we're studying a consistent axiomatic system. We're not wasting our time here proving strange results, which is, again, ultimately what Sekiri thought he was doing, right? He thought he was wasting his time proving these strange results because they were so weird. And he concluded that they're so weird, so therefore it must be inconsistent. But it's not, right? We've got the Poincare disk. So what's the Poincare disk? Well, it's the unit disk. Remember the boundary of the unit disk. This stuff that I've drawn with a solid line, remember that's technically not included. That's sort of infinity in the model. So the points on the boundary are not included. But what are the straight lines? Straight lines are just, they're diameters of the disk. So any diameter is a straight line, a straight hyperbolic line in the model. And so are circles that meet the boundary orthogonally. The really nice thing about this model is that it's what's called a conformal model in the sense that the angles you see, the Euclidean angles that you see there, are the hyperbolic angles between the lines. Right? So perhaps the most important factor of this model is even though the straight lines are not Euclideanly straight, not all of them, the angles that you see are the hyperbolic angles. But then we've got this other disk model that the textbook doesn't talk about, but we did in class. It's the Klein disk. It's very similar. So once again, the boundary is not included. I've drawn it as a solid line because, or a solid curve, because that's usually what people do. But it's understood that the boundary is not part of the model. And what are my straight lines? In this case, hyperbolically straight lines are just chords. Any old chord of the circle is a straight line. So this has its advantages. It has its advantages in that it's really easy to tell what a straight line is, right? What a hyperbolic line is, in that straightness is sort of preserved, right? If you're a Euclidean straight line, then you're a hyperbolic straight line, which isn't necessarily the case over here, right? The big downside is it's not a conformal model. This angle that I see here, that Euclidean angle, is not the hyperbolic angle between these lines. We never really got into how to measure the hyperbolic angle, but just understand that the angles you see are not the hyperbolic angles that are actually happening in hyperbolic geometry. And then we had our 1/3 model that we introduced way back at the very beginning of this course. We have the upper half plane. Which is very, very closely related to the Poincare disk in that I can imagine just coming in here with some scissors or something and cutting the boundary of this disk and unrolling the whole thing, right? So the boundary of the disk becomes the x-axis. And my straight lines are still lines that are curves that are orthogonal to the boundary, right? So I've still got straight vertical lines, because those form right angles with the x-axis. And I still have semicircles that intersect the boundary orthogonally, which in this case happen to be semicircles that are centered on the x-axis. And it's a really nice relationship between these two. You can sort of go backwards and forwards between them again and think about if I took the x-axis and I curled it up on itself to form a circle from that infinite line, then once again you revert back to the Poincare disk model. And there's of course lots more that you should know here. You should know the metrics. In other words, how to measure distances in these models. And I mean that in two ways, right? I mean that informally you should know the metric, right? You should know if I want the distance between A and B in this model, well then I'd call these boundary points P and Q. And in this case, then the distance between A and B is the absolute value of the natural log of AQ times BP over AP times BQ. How do I know which goes on top? Again, it's just the bigger values. So A is further away from. How do I phrase this? So what goes on top, is it AP or AQ? Well, it's the one that sort of has B between it. Right? That's how I want to think of this, right? So AQ is on top because B is between A and Q. And similarly, BP is on top because A is between B and P. So that's how I remember it personally. But we have a very similar metric for the Klein disk. So you should know your metrics, but you should know formally the metric, and you should also know informally what happens with distances in these models, right? You should know that the boundary is playing the role of infinity, and what happens here is this Euclidean distance that I see, sort of close to the center, is hyperbolically much smaller than these Euclidean distances out here near the boundary, right? The distances out here are very highly compressed. So if I move just a tiny distance Euclideanly, that could be millions of miles in the hyperbolic world. Same thing here, distances are compressed near the boundary, and similarly here, as you get very close to the x-axis, these distances down here are much larger. In fact, probably correspond to Euclidean distances like this that are much larger up here. All right, so no metrics. What else did we talk about? We talked about the curves of constant curvature. So these are lines, circles, horocycles, and hypercycles. Again, not discussed in the textbook. This is something we talked about just during a class one day. And We mostly talked about them in the context of the Poincare disk, but remember, circles in the Poincare disk are just Euclidean circles. So if I draw a Euclidean circle in the Poincare disk, that is a hyperbolic circle. The only difference between them is that there's the Euclidean center, meanwhile the hyperbolic center has to be seriously offset, would have to be way out here somewhere, because remember, this distance, being closer to the boundary, is much larger than a distance like that. So if you offset it very close to here, then maybe these are about the same in the hyperbolic world. So circles in the Poincare disk are Euclidean circles. Then we have these other curves, these horocycles. These are circles that are tangent to the boundary. Good question. Okay. So we had horocycles are circles that are tangent to the boundary, so they're not actual hyperbolic circles, because remember, this point here where it hits the boundary, that's out at infinity. You'd never be able to sort of do a loop if you were walking around this in the hyperbolic world. But it's the limiting case of a hyperbolic circle. And then we had hypercycles, which are circles that intersect the boundary of the disk, but don't necessarily intersect orthogonally. And the portion of this circle that actually lies in the model, this part, is called a hypercycle. And the unifying connecting theme between all of these curves is that they're what are called curves of constant curvature. Where curvature is your normal calculus 3 definition of curvature. But no, really, there's probably more here, so I'll just say, know everything. There's a lot to these models. But,
Question.
yes.
So, isn't like the hypercycle what we can see look very much like a straight line? The only difference is it's not orthogonal to the boundary.
A straight line in what sense? In the
like
hyperbolic world?
PQ we've drawn on there.
Okay.
Like those are very similar, like 2D drawings, obviously, of what is inside the Poincare disk.
Yeah. So again, if you're walking along this in the hyperbolic world, you would know that you're not walking in a straight line. You would know that you're sort of curving as you walk, but because it's constant curvature, it wouldn't feel, it would feel like walking around in a circle, I guess. So yeah, the straight line would be something like this, right? It would have to intersect orthogonally. Because this isn't, it's not a straight line. All right. Oh, there was more that I talked about here, and this is super important. I'll probably put some of this stuff on the exam. We actually proved this at the end of last class, I believe. The ultra-parallel theorem. So the ultra-parallel theorem sort of stated that two ultra-parallel lines have a unique common perpendicular between them. And you should, of course, know that lines come in two different types. We've got ultra-parallel lines, and we've got asymptotically parallel. The difference between them is that ultra-parallel lines are, these are somewhere equidistant. So there exist points on these lines where when you measure the distance between the two lines, you'll find the same distance, but they can't be everywhere equidistant because we know that's a Euclidean result. Meanwhile, asymptotically parallel, these are nowhere equidistant. And there's the formal definition, but you should know sort of intuitively what these look like in the models. So for example, in the Poincare disk model, or even in the Klein disk model, or the upper half plane model, asymptotically parallel are two parallel lines that only meet at infinity. Right? They want to intersect at infinity, hence the asymptotically part. So for example, in the Poincare disk model, here are two asymptotically parallel lines. Right, they never actually intersect, so they are parallel, but they're trying to intersect. They're trying to intersect at infinity. And so these are asymptotically parallel. Meanwhile, any of these two lines and how about this line? Those are ultra parallel or disjointly parallel because they're really parallel. They don't intersect and they're not even trying to intersect at infinity. But the important observation, the ultra-parallel theorem says anytime I take two ultra-parallel lines, so how about this one and this one, then there is a unique common perpendicular between them. It's probably something like this. And we know it's unique. There can't be more than one because if there was, then we'd have a rectangle. At the last up, we just talked about this. I don't have a whole lot to say. 6.7 was classifying theorems. Really short section, classifying theorems. Really short section. We just observed that some theorems are neutral, so they're Euclidean theorems and hyperbolic theorems. Meanwhile, some theorems are strictly Euclidean, and some theorems are strictly hyperbolic. There wasn't a whole lot to say there. So I'm surprised at how long that took. How about we just do a couple of questions? So some basic theory. How about this? Do parallelograms exist in hyperbolic geometry? So I know parallelograms exist in Euclidean geometry, right? They're quadrilaterals where opposite sides are parallel to each other. And we've done other things like this. For example, you prove for homework that even though rectangles don't exist in hyperbolic geometry, rhombuses do. So a very similar question, do parallelograms exist? And an easy way to do this would be try and draw a parallelogram, right? You have models now. So go to, for example, the Poincare disk model, try and draw a parallelogram. Shouldn't be too hard. How about I take this diameter? How about I take one line on this side, pretend that intersects orthogonally. It doesn't look like it does, but pretend it does. And how about I take another line on this side? So these two sides are parallel to each other. Right? Those two sides are parallel. Can I draw a fourth side that would be parallel to that diameter? Yeah, it shouldn't be hard at all, right? Just draw any old circle. So this is parallel to that. So the answer is yes. Here's one, proven by construction, they exist. Another answer would be just build a Security quadrilateral. We know Security quadrilaterals exist, and Security quadrilaterals are, we've proven, are parallelograms. So yeah, lots of ways to answer this. One is to actually just draw one. One is to say Security quadrilaterals are parallelograms. So part B is in Euclidean geometry. In Euclidean geometry, the opposite sides of a parallelogram are congruent. So, is this true in hyperbolic geometry? Again, a couple of ways to answer this. One is you could go to Security quadrilaterals, and you could say, hey, we've proven that the summit is always longer than the base. Right? So the answer is no. The opposite sides are not congruent, because I know in this example that the summit is longer than the base. Another way is come back to your drawing, and I have a finite length here. Right? I have a finite length and a finite length here. And maybe in this picture, maybe in this parallelogram that I drew, maybe these are the same length. They're not, but maybe they are. What I can do is just form another parallelogram using this same side length, but I could make the side length up top here as long as I want. In fact, I could sort of think of the limiting case as taking these two boundary points, and that really doesn't look orthogonal, and taking the circle that intersects here. And of course, this is not a parallelogram right now because this point is off here at infinity. But if I just move it in just a tiny bit, I can make this top arbitrarily long relative to this side. So I can definitely form parallelograms where opposite sides don't have the same length. So the answer is no, it's not true. And C, is this true in neutral geometry? And in comes some basic, just some basic theory here, some basic logic. What would happen if it was true in neutral? Remember, neutral theorems are both Euclidean and hyperbolic at the same time. Right? So if it was true in neutral, it would be true in hyperbolic geometry. It's not true in hyperbolic geometry, therefore it's not a neutral result either. So the answer there is no. We'll just do one more really quick one. Just getting into metrics and making sure you understand how these models work. So to find a triangle in the Poincare disk model, for which the perpendicular bisectors of each side do not intersect. So try and draw this. Again, it's going to be a sketch. It'll be an intuitive sketch because we're not working very precisely with a metric or anything. But as long as you sort of intuitively sketch the idea that distances are compressed near the boundary and whatnot, try and draw a triangle. Draw a triangle for which the perpendicular bisectors do not intersect. Right, and some do. For example, if I drew this triangle, and I took the perpendicular bisector, so the perpendicular bisector of this side looks like probably something like this. Perpendicular bisector of this side probably looks something like this. Then they're intersecting. And I'll give you my idea, is let's essentially take a right triangle formed along here. What's the perpendicular bisector of this side? Is it something like this? The answer is no, because this sort of, yeah, this looks like a hyperbolic line, but this is the Euclidean bisection, right? This is halfway along Euclideanly. Hyperbolically, the halfway point is somewhere way higher up here. Right, so my idea is, let's take a right triangle where I push this boundary point way out near, or this end point rather, way out near the boundary. Right, then what's the perpendicular bisector of this side? Well, the midway point of this line, hyperbolically, is probably, somewhere way out here. So the perpendicular bisector of this side would be something like this. Does that make sense? Right, and then do the same thing over here, just push this end point out really close to the boundary so that the perpendicular bisector of this side is again some really small Euclidean semicircle. I shouldn't say semicircle, but again, the halfway point of this line is not the Euclidean halfway point. The hyperbolic halfway point is somewhere way out there because distances are super compressed. And they already, these two perpendicular bisectors already don't intersect each other. Now I just have to complete the triangle, drawing the rest of it. That curve is I can't stand this curve, I need to erase it. Let's just try and draw a better circle. What's the perpendicular bisector of this side? Well, the midpoint is exactly the Euclidean midpoint that you see. Would be somewhere around here, and intersecting this orthogonally, because this is the center, it's just it's just this straight line. So there we build one. And again, the idea behind building this sort of came down to understanding the metric and understanding the distances are highly compressed. So those perpendicular bisectors don't intersect. By the way, one more thing I'll point out is that, what am I trying to say? Remember from geometry 1, the intersection point of the three perpendicular bisectors, that's the center of the circumcircle, right? So because they don't intersect here, there is no center of the circumcircle because this triangle cannot be circumscribed. How do I know that? Well, because they don't intersect, but also remember, circles in hyperbolic geometry, at least in the Poincare disk model, are Euclidean circles. And there's no the Euclidean circle that I would draw that circumscribes this, that passes through all 3 points, probably looks something like that. And that doesn't live in this hyperbolic model. So this triangle cannot be circumscribed. And in fact, to answer this question, if you drew any old triangle that can't be circumscribed in the hyperbolic model, then you'd have an acceptable answer. But now we'll stop here, and that's actually the end of class, so pretty good timer. We'll start on elliptic geometry on Wednesday, but it won't be on the exam. And yeah, I'll see you Friday if nothing else.